Hi everyone, my name's Dean Howe, and firstly I'd like to thank SAFE for inviting us to talk at this World Fair this year. I'm going to be talking a little bit about juggling unstructured data between CAD and GIS, and just a few lessons learned along the way. So it's more of a, tips and tricks, some technical stuff. I'm not delving really too deep into actual FME, but just how it works and how it worked for our project. As I said, my name's Dean Howe. I'm an FME consultant. I'm a GIS professional. I've been in the industry for close to 30 years now. Worked all around Australia and around the world, and now working with Locus on a whole lot of FME projects. And thank you to Locus for also asking me to do this presentation here today. So today what we're going to be talking about is some JML, some juggling macro language. You're probably asking what is that? So I'll enlighten you shortly. We'll look into more detail about unstructured data, CAD and GIS. We'll look at using standards, quantity and quality. We'll look at performance tip that I'll give you, looking at custom transformers, multiple developers and the pitfalls of that, and just a quick conclusion, and then questions at the end. So hopefully that will make sense as we go on. So Locus started in New Zealand, but they've more than 10 years now helping organisations with their data challenges. I'm based in Adelaide in Australia, but the team across New Zealand, Australia, and helping organisations worldwide. There's a number of certified professionals which work with Locus at the FME desktop level, server and trainers. So we're here to help with all of that FME side of things. So, all right. So let's jump into the maths behind juggling. I guess it's probably one of those strange questions you've probably never been asked before. And you probably also go, well, is there really any maths behind juggling? But juggling and spatial data have a lot in common in that, we're talking about patterns and cycles and correlations of how data fit together. And so there is a lot of similarities there. But the maths behind juggling is actually quite complex when we think about it, because it comes down to how many balls or how many objects are we going to be throwing up, how many hands are we using, are we just using one hand, we're using both of them, or we throw them overhead and we're doing whatever, and so are we using different size objects? I've seen people do watermelon and a tennis ball and all those sorts of things, and that adds to the different weights and different velocities and different heights and all those sorts of factors. So the maths behind juggling is actually quite interesting if you really wanted to look into it. Do jugglers really care? Well, some do, but most don't probably. And but there's probably some rationale in that jugglers probably should care a little, in that if you're just a occasional juggler, you probably don't really want to go into it. But if you get more and more experienced and want to do more, juggle more and more things, and then you probably want to be able to understand that maths behind it, so you can implement it in your mind more than anything else, and then get the mechanics. Do mathematicians really care about the maths of juggling? Well, I was actually surprised in that that there is an amazing amount of information out there from mathematicians studying juggling and the maths behind it, the patterns and all those sorts of things. And so yeah, a lot of mathematicians look at that and see how that relates to different other things. And so if you're really interested and need some good bedtime reading, then search juggling and maths and you'll find lots on the internet. Do I care about the maths? Well, to be honest, probably not really. But for this, the thing I do care about is that spatial relationship. And the more you look at juggling, the more you look at spatial data. It's amazing, that correlation. And that's my passion, is in GIS and spatial location. And so in that case, I care about how they relate to each other. I care about what we can do with it. And it sort of adds a good synergy for my presentation today, how we juggle physical things and how we juggle data as well. All right, so let's look at JML, and I mentioned that before. I bet you not many people had heard of JML before, a juggling macro language. So if you look at on the left, it's just another variation of XML. And so if you have used XML in the past, or have looked at an XML document, you'll see just the normal structure there, and so it enables programmers in this case to actually program how to simulate juggling. And in this XML, we've got the type of thing that's going to be juggled. So we're juggling a ball, but it could be something else. We're juggling what sort of path it's doing, how many hands we're doing, what position it starts, and all those sorts of things. And so there's a lot of actual information in that XML, but the main thing is when we look at it, we can, this sort of simple one, it's just juggling 3, and so the simulator actually is created from that XML, and how we can actually see that relationship between the X and Y events as they're moving along. All right, so that's a bit of fun leading up to what we're actually going to talk about today. And so we're going to talk about unstructured data, CAD and GIS. And my background's in GIS. I've used CAD a lot as well, but I've used GIS around the place. And I guess the main difference, and this is really just my definition, so there's, it's very debatable, but the difference between, a GIS is normally points, lines, and polygons with a database or attributes associated with those points, lines, and polygons. Whereas a CAD drawing doesn't necessarily need to have those attributes associated with the feature. So it could be just a raw drawing, points, lines, and polygons again, with some text on it, but that text has no real connection to the line except that it's drawn near it. Whereas in a GIS, we might use an attribute to actually label the polygon or label the line. Whereas we don't have to do that in CAD. We don't have to do it in GIS either, but it's more structured. So the GIS tends to be structured. We have a database there. We have a table where you define the features. Whereas a CAD, you can, in a CAD drawing, you can have lines and points and polygons all on the one layer, and you can have some text on that same layer. You can then have another layer which has the same lines, points, lines, and polygons. Whereas in a GIS drawing, we'll have some point layers, we'll have some line layers, we'll have some polygon layers, and normally the way you would do it is, all of the lines of a certain feature will be on one layer. So they might be spot heights as an example, and then you'll have a contour line, and then you'll have a lake or whatever as an area feature, and a river as a line, and all this. And they tend to be on different layers, so we can then analyze them a lot easier. Whereas CAD doesn't have to be that way. So let's look at some examples of CAD drawings. Here we've got a drawing where we've got some arrows in there, and so we're going, all right, is that, we can sort of look at that visually and go, all right, the arrow points out to the 3 as an example, and that's a distance, and the 190, 57, 30 is we'd assume that's a bearing, but they could be on the same layer. And then we've got two different blue lines. We're going, all right, well, what does that actually mean? And we've got some text in brackets. What does that mean? And so it can, and spatially, where is that? CAD drawings don't have to be spatially located correctly. They may well be spatially dimensionally correct. So a 10-metre line is 10 metres, but it might be centred over Antarctica as opposed to over Adelaide. Here's another CAD example where we've got 27.92 and we've got a 4, and they're both sitting over the same line. We're going, all right, if I looked at that, I can see that the 4 relates to the lighter blue line because there's other 4s around it, and so I can make that assumption. But in that case, the 27.92 is actually closer to that blue line. So is it related to that? And so we actually have to do some tests. We have to go, all right, how long is that line in real-time space? Now, if it wasn't actually in real space, then how do we actually determine that? Whereas with the GIS, it's a bit more structured. Often, it doesn't have to definitively be, but here we need to do a lot more testing to actually make sure it's okay. Here we've got some other data. What does the underline under the text mean? Is it upside down mean anything? We've got a bearing in the middle of the road. What does that actually mean? What layer is it on? The 15.24 is telling us how wide the road is. Now, you might know those things, but how to program FME in this case out to figure that out is another thing. Orientation of a CAD drawing. Often in a GIS, the north arrow is connected to the data. So as you rotate, for a map, if you rotate the data, the north arrow will automatically rotate with it. With a CAD drawing, the north arrow is just another symbol on the drawing. It doesn't actually have to be connected to anything, and therefore you could actually get the north arrow pointing in one direction and the data being in a totally different orientation. So how do you actually figure out which is right, which is wrong, is that easy enough to do? Here we've got another example where we've got data over the top of each other, and the thing in CAD, we've got the concept, or certainly AutoCAD, we've got the concept of paper space and model space. And so model space is in that real world coordinate system, but it still doesn't need to be in the right geographic location. And then we've got the paper space, which is the how it should look when it's printed. So in this case, we've got text at lots of different sizes overlapping each other, and that's because in the paper space version, we're going to say, all right, only show things at a certain scale, only show these layers and whatever. Here's another example where we've got this is actually a multi-story building, but the way it's been drawn is one of them might be correct, but they've then just done the copy of the base, moved it over to the side. So the second one's actually now spatially incorrect because it's not the property next door, it's the property on top of it. And so if we had that in a CAD drawing, we could turn off level 1 and just see level 2. And so whereas within the CAD drawing, in this case, they've shown level 1 and level 2 in two separate spots. So it just makes it a bit more tricky to validate and to understand it. What can we do to actually make that unstructured data more structured? And this is where we can use standards. So here in Australia, we have the Australian standards, and I've just listed a random one there, the AS 1100, which is for technical drawing. Doesn't really relate to this project at all, but just interesting if you want to read it. We've got Standards New Zealand, so they're the authority in New Zealand. So there's one SN HB3, which is just another technical drawing a standard. And then what you'll find is, depending on your industry, who you're actually drawing for, all those sorts of things. So here in South Australia, we have SA Water, and so they have requirements, a document called Requirements for Technical Drawings, TS 0100, SA Power Networks, using a similar terminology for a technical standard, TS 099. And, it just goes on. Almost any entity that is accepting a drawing, whether that be CAD drawn drawing or a printed version of it or an electronic version of it will have a standard. And underlying that is probably the crux to how we actually can move from having data which is unstructured to moving slightly closer to being in a structured format. And a lot of CAD packages are now moving more and more closer to GIS. So you can actually add attributes to a line in AutoCAD as an example, but it depends on the use of it. So if you have no use to actually analyze that data, you're just drawing it because you need to lodge it to an authority, then why would you attribute it? And that's where GIS and CAD often are very different. GIS data is often used for analysis in a lot of cases and map production and those sorts of things, whereas CAD tends to be, it's computer-aided drafting, and so it helps people produce their drawings for whatever authority that they're doing that for. So here we've added an extra ball into the simulation, and so using that standards, we could start to do a little more, but we're still going pretty slow, and we're still struggling to actually get it to match exactly the way we want to. But it's moved us a lot closer. All right, so we've now gone from a more technical side of things, some observations and analysis on my part. Now we're going to delve into some FME side of things and quantity over quality, and that it's a really interesting thing, because if you read some safe documentation, they will recommend keeping the number of transformers in a model as small as possible, and I agree there 100%, but it doesn't always work. So in the project that I worked on, we had a number of workbenches that varied from, in this case, one of the smaller ones had 134 transformers, nice and simple, but 134, and it adds up really quickly once you start, you got data in, you do a bit of manipulation, format it a bit, and then output it. You very easily get 20, 30, 40 transformers just in a very short period of time, and then you start adding some to complexity. And so another one had 183, and then we jump to a huge step. We had 948 transformers in a single model. And so once we start getting up around that quantity, we start to then have performance issues. And our main model for this particular project had 3,869 transformers. And so can you imagine trying to manage that, trying to maintain that, trying to actually understand it if you had never seen it before. So huge numbers of transformers in a single model. And so understanding that quality and quantity, we're able to then juggle a little more. We're able to use the functions within FME to actually give us a better idea of what we're actually wanting to achieve. So one of the big things that I would say is that we actually want both quantity and quality. Quantity from a number of workbenches. So the more workbenches, the better in a project, in my opinion. Don't try to cram it all into one workbench, but we want quality in each of those. And so when we have that combination, and now it's not always possible, there's prime example, 3,869 transformers. That's not a great number to try from a management point of view, or maintenance and all those sorts of things. That just makes it hard. So if we were to do it again, we'd probably break it down into more and more parts just to be better off. Here's a snippet of that model, the 3800 model, and this is just a snippet. And within FME, I press the extent button, and FME doesn't allow me to zoom in to the entire model just because it's so big. So you sort of have to get to this scale and then still pan and zoom or pan around to get to the other parts. And that's probably just a couple of hundred in that snapshot. But what we then did, and it's one of those performance tuning things as well, putting things in bookmarks and having bookmarks in bookmarks, helps you to, one, understand what's going on, from a good authoring point of view and maintenance point of view. But it also helps it to, so you can run and test individual parts of that model. So you can just run that bookmark or run that number of bookmarks or run to that bookmark as opposed to, run to an individual transformer. But yeah, it's crazy how big that got over a fairly short period of time. All right, so my performance tip for today and for this presentation is around attribute management. There's lots of data and lots of white pages and stuff on the FME forum about performance management, but this is one that is really stood out to me during this project. And at one point we just found that 3800 model was taking 15 minutes to run, which might not sound like a long time, because I know people who have models that take multiple hours to run. And when you look at the number of things it's trying to do, it's got 3,800 things to run through. You would think 15 minutes probably okay, but we started to go, it's starting to really, we noticed it getting slower and slower as we put more and more in. So we started investigating. And what we found is that when you're developing, it's very easy to just let the attributes flow from one transformer to the next. And very quickly, you've got a transformer that's processing 100 attributes, and it only needs 2 of them. And so we went through a process of actually using Attribute Manager, Attribute Keeper, and a number of other transformers in the project. And what we found is that 15-minute workbench went down to 2 minutes just by getting rid of attributes that weren't necessarily in the project. So we've literally got tens of the Attribute Keeper transformers throughout that big model, just culling attribute. We'll use the attribute and then cull the ones we don't need, and then set both Attribute Manager, Keeper, and the others. And so in this case, we've got just 3 attributes that we kept. We kept the AutoCAD space. That's an attribute from AutoCAD telling us whether it's in model space or paper space. The order that, so the tab order for us was its page, and then what business object we were processing. So they're just sort of things that we kept, and they flowed on. We did have some issues where, every now and then we did an attribute keeper and we didn't keep an attribute that was needed further on, and something would break, and we'd fix it up. But overall, once we finished those, then it gave us a lot more confidence that we could fine tune and the model would run so much better. So now, we're juggling more balls, keeping them in the air longer, and we're getting good performance out of it just through those simple things. And so if you're getting performance issues with your model, I would certainly recommend just searching the forums for performance, taking on some of those recommendations by SAFE and by the forum members, because there's so many of them there, and so many of them, just that fine tuning just helps you so much. The next performance thing that I certainly highly recommend is custom transformers. So when we're looking at the project, in essence, was taking in a CAD drawing and then validating it against a standard. So what we found during the proof of concept is we had all these little modules which were doing exactly the same thing. So reporting, mapping, validation, all doing those sorts of things. But we repeated the transformers. And so what we then did is had a process where we went through and actually converted all those repeatable actions into custom transformers. Now the benefit of that, and in the coming couple of slides we talk about multiple developers. The benefit of having those custom transformers is that they can be then shared between workbenches. They can then be shared between developers. So If you're one developer is working on one workbench, but they might just, what they need might be in that custom transformer, they can just edit that custom transformer or utilize that custom transformer and not bother that other developer. So the benefits of custom transformers, consistency of programming. I don't know how many times I've seen developers, where they'll misspell something, or the formatting of one part of the report is different to the other, and you're just going, why aren't you guys being consistent? Now, by using a custom transformer, they only have to do it once, therefore actually remove that consistency problem, because all of the variables are done in one spot. Testing. The other great thing about custom transformers is that we can test in isolation. So you can publish that custom transformer, open it up in a new workbench, test it to your heart's content, and you're actually not affecting the other developers, the other testers, or anything like that. Maintenance. So if we want to look long term, often the people doing the development aren't the people doing the maintenance. So we have that big model, and I dread the person who's going to have to maintain that, because it's just huge. I wrote a document when it was at about 1,500, and that document was multi-tens of pages, just trying to explain how the model worked. So from a maintenance point of view, custom transformers make it really easy, because you can, once again, isolate that bit of programming. You can if you go, oh, why is this not working? And then look in the transformer, fix the transformer, publish it, and then so you don't have to go and publish the whole thing again. It also speeds up development. We talked a little bit about it already, that we have multiple developers utilizing the one custom transformer, and still can only have one developer changing it, but we can have multiple developers using it, and that becomes really quite efficient when we want to do our when we're getting to big projects which have lots and lots of developers. So here are a couple examples. A map generator we created. Now we've literally got hundreds of these in that big model. So the actual transformer number is probably so much bigger than 3,800, because we're looking at hundreds of these as well, which might then have lots in it. So we have a status one to make sure that the statuses are consistent. Have you seen that, where someone will type just type a attribute incorrectly, and then that flows on, and you go, why isn't this working? Well, using a custom transformer, the status is always the same. Base map builders, so the same base map is being built all the time, and that's what we were finding once we were doing the reporting. We were going, why isn't this part the same as this part? And so once we created the custom transformer, those base maps were spot on all the time. All right, so we're now able to juggle a lot more balls in the same amount of time. We're now more confident in what we're doing, because of all those pieces that we're putting together. All right, so I did just briefly touch on this, but I thought it's one of the last things I'm going to talk about, but and that is versioning within FME, and versioning with FME server. I'm a big fan of that. It helps to keep the models when they're published, and so it's going in. But the biggest problem I see with FME, it doesn't allow multiple developers to work on a thing at one time. Now, you probably come back to me and say, well, why would you want to do that? But what we found is that when we were trying to prioritize functionality within the project, we also had to figure out the workload for individual developers. So we had to make sure that developer one had enough work over here and developer two could do over there. And sometimes it was just really difficult, and you might end up with a developer just sitting doing nothing, and that makes it hard. So when we do that custom transformer type of thing, we can actually then say to those different developers, all right, you work on this custom transformer, and that'll need to do this, so I can then use it in my model here. And we then can do that. So versioning with FME service, some organizations will use, GitHub and those sorts of things, but it's a real tricky juggle with multiple developers, and we always want to try and see what we can do to improve that. And I certainly think that custom transformers is one of those ways. So it's just another little graphic. Now we're getting multiple people involved in the whole process. We're having to juggle that data, juggle those processes, juggle those workbenches for everyone to use. All right, so I appreciate your time today. We'll come up shortly for some questions, but enjoy your time juggling the data, and look up all the maths on juggling online. You might be surprised. All right, so thank you, and I thank you to SAFE as well for giving us the opportunity to be here today.